Hey robot makers, how you doing? Hope you're having a good day so far. So do you want to learn about how to make a machine learning model and how to identify objects in a scene in an image? Then this is the show for you. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code and have a whole load of fun along the way. So let's get straight in, shall we? So this is all about object classification. And we're going to be using quite a few different bits and bobs today tool-wise, but all in one web browser. So we're using Colab from Google. So let's have a look at the overview of the session. So this is part of the series about building your own AI assistant. So today we're going to be looking at how we can extend our AI assistant. So I've got my companion next to me, just over here. So this is Sonny. He has a webcam for his eye there. We're going to be using that webcam later on in this series to be able to give him machine vision. So I've previously used this camera to do some object detection, but I want to sort of back up a little bit and show you how you can do this yourself, because you can do it in a web browser, which is pretty awesome. So we're going to be looking at Google Colab, which is this web-based Python environment for research and learning. It's completely free. We're going to build a machine learning model today using the hello world of AI machine learning models, and we will learn all about that. We're going to take a collection of images, we're going to train our AI, we're going to test it out, our classifier, and we're going to do some quick channel updates at the end as well. So let's get straight to it. So what is this Google Colab? So like I said, it's a web-based Python environment for research. If you've ever used Jupyter Labs, it's basically Jupyter Labs with a kind of a bespoke version of that for doing machine learning research, data science, that kind of thing. So it's ideal for machine learning. They've already put all the libraries part of the system, so it's very easy to use them. It's kind of what am I saying there? It's rebuilt for use. I don't think that makes sense, does it? It's built for use with TensorFlow and Keras. Now, if you've never heard of those things, don't worry, we're going to cover them off today. And also Pandas and NumPy, if you've not heard of them as well, that's something probably for another show, but this touches on them. So Pandas is a data science library. So it's a whole suite of different tools that you can use in Python for manipulating large sets of data. And NumPy is a similar kind of thing, but with a different set as well. So you can create things like data frames, similar to like a big data warehouse or spreadsheet, and you can slice and dice and pivot all that data in code. So yes, you can head over to collab.research.google.com. We're going to be having a look at that shortly when we do our demo. And it's free, it's very easy to use. You can start cutting code on this today, and they've got loads of tutorials, and in fact that's what we're going to be going through today, is one of the tutorials. So how does machine learning actually work? So how does image processing work? So say we have a scene, we have an image. So there's a picture of my Sonny on the backdrop behind me, and we're going to take a picture of this using a digital camera, and that's going to slice that image up into pixels. It's going to use some kind of CCD device to capture the image and convert it into pixels. And those pixels are going to be RGB. They're going to be red, green and blue values, and each value is typically between 0 and 255 if you're using 8-bit image, which most cameras do. But for machine learning, we don't really care about all the colours in our image in this particular use. We want to just use grayscale. So we're going to convert each of them images just to a value between 0 and 255, black and white. And then what we essentially do is treat that image as an array of values. So we're going to sort of unpick that and have a really long array, and that will represent our image. Because when we detect objects, counterintuitively, you don't actually look for an object in the image. The neural network does all this through kind of a fuzzy logic, and it's really intriguing that it can detect things very accurately using this, because our eyes and our brain, we think of objects as being something, sort of a shape in an image, but computers don't understand shapes. They just understand zeros and ones, and we have to be able to make a model that can use that to detect objects. So we might also reduce down the number of pixels, the resolution, so that we again make this quicker to process. So the data set that we're looking at today uses 28 by 28 pixels, so very, very small pixels from a very large picture in effect. And we'll have a look at that shortly. Okay, so image processing. So images are just arrays, just as we've seen on the previous slide. And for each of those pixels in that array, they're essentially a value between 0 and 255, which is 1 byte in computing. So the darker the image, the lower the number, the higher the number, the lighter the image will be. So 255 is like white and 0 is black. As you can see there. Actually, I don't think that's very accurate representation of those values, because 16 should be very dark and 185 should be the lightest, I think, in there. I think I did that by hand. That's probably why it's like that. Sorry, was there something else on that slide I needed to say, actually? Let me just have a look. So we've gone through that, sorry. I had to backtrack a second there. And I've got this on a slight delay there as well. Let me know if the sound's okay, Rob, as well. I had some issues with my audio a while back when there was a new release of Ecamm Live, and it messed up all of my sound settings. No, I've covered everything off on that slide I needed to do, so that's great. So yes, if you like these videos, if you want to help me grow the channel even more, give this a like on Facebook or YouTube. Both of them count to the popularity of the video. Leave me a comment as well. That always all helps, whether you're watching live or on playback. Helps with the engagement. And if you've not subscribed to the channel or the Facebook Small Robots group, do that as well. So Rob says, yeah, sound's coming through great, fantastic. I'm always worried about bits of distortion and stuff, and just the distance I am from the microphone. Cool, okay, so I also have a new video every single Sunday. So I go live every single Sunday. In fact, I have a special call to action for that, which is this one. So yes, every Sunday around about 7 o'clock. I used to say GMT, but we're in British summertime now, so that's messed up all my slides. So it's 7-ish, depending on what the local time is in the UK. But you'll know roughly where you are around the world. I've already had somebody, was it Ray, who was saying, this is 4 o'clock in the morning in Australia, which, sorry. I'll try and do a later stream at some other point in the future. So that's the video, and we also have a call to action for the website. So if you've not visited smarsfan.com, I've actually updated it since I did this little graphic. So there's now a learning platform on there. So if you want to learn Python, robotics, how to build a SMARS robot, either the quad or the walking version, you can head over to SMARS, completely free. And there's some tutorials on there as well as some code. And also, if you want to help out the channel, pay for all this stuff that I have to spend lots of money on, ridiculous amounts. Quite a few of you have already started doing this. So you'll help pay for the hosting, the royalty-free music, the graphics software, the streaming software that I use, and all the equipment as well. And from today, seeing as we've had we've reached the threshold on YouTube for monetization, we can do things like super chat, and we can do emojis and things. So if you look in the chat window at the moment, you can see at the bottom there's a little smiley face for emojis, and you can do things like the code emoji. So if I just type code down there, you can probably see that come through. We have the little Python, and we have the little snake as well. And essentially what you type in, if I just press that, so if you type :_code and then code, or :_snake : or :tongue : you'll get the different emojis coming through. And super chats is a way of essentially just giving a tip to the show as well. So I've not got very fancy graphics for that yet. I am actually working on something in the background, and we'll get back to the show content in a second, but I just wanted to show you this. So if I just go back to me, and if I just pretend that somebody has given me a super chat, we get a little graphic up there and a little sound. I need to make them a bit more interesting, because that's a bit poop at the moment. So that's that. I just wanted to show you. Okay, so let's get back to our content. So what is a neuron? So in neural networks, it's modeled on how the neurons in the brain actually work. So you have all these interconnections between different neurons. You have inputs, you have outputs, and you have these things called weights, which allow you to it's like a valve you can turn to sort of make something more or less important. And we use them valves to make something more or less important during the training part of the model. So here's an actual slide of some real human brains. This is the, Golgi-stained neurons in the human hippocampal tissue. And if we look there, there's some neurons, there's some inputs, and there's some outputs. So neural networks are based very much on the brain structure and how that works, because it's very successful. So how do they work really? So it's just lots of maths behind the scenes. So each neuron has an output, and that's connected to the input of the next layer. So they call these layers. The layers are kind of the vertical drops of these, and we'll see more in a second. The number of layers and the number of neurons can define the sophistication of the neural network. But the more you have, the more processing power you need available too, and the more memory to store all these different interconnections. So the connections are weighted. These weights are adjusted during the training phase, and that's actually what makes the neural network work. So we'll get into what these blobs mean and these connections mean, but just picture this in your mind. And we call this the input layer. So we connect our image to the input layer. We have these hidden layers. We've got 2 in this particular one, and then we have an output layer. On the output layer, what we are actually looking for is, given any image, we want to know what the classification of that image is. So is it, we're going to be looking at some data in a minute of clothing. So we want to know, is it a shoe? Is it some trousers? Is it a shirt? Is it a bag? That kind of thing. So that's what we want to get. And if it's not sure, we want to get a percentage. So how confident is it actually that that it's detected this thing? Okay, so let's have a look at how does it really work. This is the full model. So we've got our layers there. We can see we have our oops, our data. Let me just back up a second. Let's try that again. So we've done that bit. No, we've not done that bit. I'm jumping the gun there. I just have to let it go through it to do that again. Right, here we go. So this full model, yes, down the side here, we have these numbers represent the pixel values between 0 and 255. Remember that grayscale? And we split up the image into all the different rows and split it into a very long thing, and then we kind of tilted it on its head there. So on this particular example, I'm saying 4 values are an input into the first input layer for the first node in our neural network. And then the next 4 go into the next node, and the next 4, and they're all in the input layer. And then each of these input layers has connections to every other node in the next hidden layer. And they have a connection to every other node in the next hidden layer. And then they all have connections to the output layer. And what we're going to do when we train our algorithm, we're going to come across here, and we're going to change these connections. We're going to change the weight of them. And the weight is essentially another value that we're going to store, and we're going to change the values of those each time we run our training thing. And when at the end of our training, we will get a result, and we can see how accurate it's guessed against the training data. So we have 2 sets of data. We've got our training data and we've got our test data. So we run our model against the training data, and then after we've done that, we then check it with our test data. And the model has never seen the test data. And the idea there is that you can make sure that your model is working accurately because it's never seen this data before, so it's not able to sort of adjust for it, and it's not over or under fit for it. We can have a look what all that kind of stuff means too. So that's the kind of full model. We'll come back to that in a more practical sense in a minute, but again, that's just to sort of enable you to visualize what's going on there. The training algorithm depends on which model we're using and what we're looking for. So neural networks can be used for all kinds of stuff. It could be voice recognition, it could be object detection, object classification, it could be word classification. There's all kinds of different things, and depending on which use you're using, you'll use a specific model and training algorithm. So how does machine learning actually work though? So here's our little neuron again. And what we do is, for each of these inputs that we're bringing in, remember they're the pixels between 0 and 255, we then have a weight, and we have weights for each of these neurons. And this is the thing that we can tune with our training algorithm. And essentially, that's another number between 0 and 1. And we're going to multiply each of the inputs by this weight to get another number. And then we add the product of all those calculations together so that we get another number. And then that number is too large. That then needs to be changed to a number between 0 and 1. So we have to use something called normalisation. And there's a special function that we can use that will do this. A very clever mathematician called Euler came up with this. So we use something called the Euler number. So a sigmoid function basically takes in a number, and we use the Euler's number to basically use that little formula there just to multiply things out so that we get a very small number between 0 and 1. And it's very accurate at doing that. So given any size of number, it can then convert that to a value between 0 and 1. And I'll come back to your questions in a second, Ovi. I know you got some good questions as well, so I'll come back to them shortly. So in this example here, the x is the result of the calculation that we did in the previous step. So adding all those different products together from the weighted values that we multiplied, we ended up with 186. So we then stick that in here, and then we get a number between 0 and 1 that we can then feed into the next layer of our neural network. So that's the calculation, that's the guts of neural networks. That's the thing that's going to crunch over and over and over again to get us our model. So there's these things called tensors, and it's one of those things that's like, what is this? So the software that we're using is called TensorFlow, and the flow is through the model left to right. So what is a tensor? So if this is our neural network stuff, all these things here are tensors. Wherever we've got an array of numbers that we're going to do some operations on, those are, as the description there very eloquently says, in mathematics, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects related to a vector space. That's quite a mouthful and quite a lot to unpack there, but essentially it's just arrays of numbers that we can perform operations on. And that is what we need to do with our weights. We need to take all those different inputs, so the 28 by 28 pixels all stretched out in a big array. We need to take each of them numbers, put them through, multiply them by the particular weight for that neuron, and then put the output of that into the next neuron, and so on and so on. So each of those arrays of weights and numbers are tensors. So we can visualize this a bit better. I always think about, what does a single dimensional array look like? So you're used to this, it's essentially just a list of things, like a bit like our image array before. A two-dimensional array, that's like an image, so we've got numbers going across and down, rows and columns. And then a three-dimensional array is like a cube. This is a multi-dimensional array. Now you can have fourth, fifth, sixth, n-dimensional arrays, and that's what tensors can be used for. So a tensor is just a way of capturing all those different numbers in a structure. And we actually talk about the shape of the tensor, and we'll have a look at an example of that shortly. So this data set here is the hello world of AI. So this is the Fashion-MNist Dataset, and there is 60,000 images and 10,000 for testing. Sorry, there's just a Twitch thing that's come through here that I need to kick off, but I have no idea how to actually kick that off. How do we block that? I have no idea. I'm going to have to figure out how to do that later on. Ignore that Twitch thing. You might not even be able to see it. Okay, so yes, we've got a data set, 70,000 images, 60,000 for training, 10,000 for testing. And this is what they look like. So they're black and white pictures, they're grayscale, they're 28 by 28 pixels, and they have labels. So we can see there's the t-shirt or slash top, there's trousers, there's pullovers, dresses, coats, sandals, shirts, sneakers, bags, and ankle boots. And you can see there the labels correspond to an index that we're going to use later on, so 0 to 9. And then we've got the description of the label that we're going to categorize against. So they've made it really easy in the Colab environment to play with this data set. It's a huge data set. And it's also a standard, so that means that we can benchmark against things. Benchmark one algorithm against another. So here's our 28 by 28 pixel grid. This is an example from the dataset. You can see each pixel there has got a value between 0 and 255. There is 6,000 training images of each label type. So for trousers or t-shirts, there's 6,000 for each of them. And there's 10 labels in total. Okay. So let's have a look at our test and training process flow. How does all this actually work? So we're going to prepare our images for the model. And I can show you some examples of where I've done that in a second. We're going to load those images into our data model, into our TensorFlow. We're going to fit the training model, and that's the actual training of it, running the algorithm to adjust all the weights. We're then going to test the model with our test data. So we're going to put in an image it's never seen before and see if it will correctly predict the outcome of that image. So has it guessed the label correctly? We're then going to adjust the weights and keep doing that until the results are acceptable. And that means that the accuracy is what, 0.9, again, a number between 0 and 1. The more accurate, the longer it might take. And you can actually make your model less accurate if you run it for too long, because it kind of overfits the model for the training set that you provided. So you can see there, we're going to come down here after starting off this. We're going to collect our images for our data set. We're going to prepare them. So let me show you what preparing the images actually looks like. So I have, if I just come out here for a second and just get my screen ready. So I created a project called TwitcherPi, and the premise of TwitcherPi is that there's a bird table outside my summer house. I'm going to point a Raspberry Pi camera at that bird table. It's going to look at the birds on the table. It's going to count how many birds of each class, so how many sparrows, how many blue tits, how many robins are on that table at any given time, and then it can write that to a database. So how do I make this actually work? I need lots of pictures. So let me go back over to my screen share for a second. So if I just make this a bit bigger here. So I downloaded, was it 1,000 pictures? So 100 pictures. Yep, 100 pictures of each type of bird that I wanted to classify. So I've got a black bird there, for example. So I didn't check on whether these were royalty-free pictures or not. So this is why I can't share this particular set. But I'm hoping to get this project up and running to a state where I can actually share the data from my actual bird table once I've got that up and running. You can see there we've got 100 images for each different type of classification. So I've got blue tits, got chaffinches, goldfinches, great tits, house sparrows, long-tailed tits, robins, starlings, and wood pigeons. Let's see our wood pigeon there. So these are color images. They vary in size and resolution. So what we need to actually do here is we need to do a couple of things to prepare it. So let me load up this tool here. So this piece of software is called Label Image. It's a free piece of software, and it enables you to open up an image, and then you can create a rectangle by just going like so. So this is going to be where the image resides. So like so. And we're going to say that this is a wood pigeon, and it's now added wood pigeon to this particular image. There's a label that's been defined for that. And when I save this out, it will save it as an XML file against that particular image. And what we'll use another utility that will gather all them XML files, create a CSV file, and then that CSV file will be read into TensorFlow as the image array and the classification, as the labels of each of those. So that's very tedious. It took me an entire weekend to download 1,000 pictures, 10 of each bird, 100 of each of the 10 birds that I decided to classify. And I then had to spend another couple of days just dragging rectangles. Some images have multiple birds in them, and I have to classify each of them. So that's what we mean by preparing it. I didn't, in this example, scale down the images beforehand, and because I didn't do that, it took 3 days to train the model. So that's insane. We'll see how quickly we can train a model in a second. But I wanted to show you this. This is something I did start doing, and it does work. So let me see if I've got an example that I can just share with you. Just bear with me. I'll show you the results of when it's classified an image. I think if I go to here, images, bird table. No, that's not it. Where's the output gone? I'm just trying to find the result from one of the runs that I did with this. I'm sure it was on there. It's not that one. Models, research, object detection. No, it's not that one. I should have prepared this beforehand. Is it under images? Nope. Ah, well, never mind then. Well, essentially, it just draws a rectangle and says as a label what it thinks the image is in a particular set. So I did the same thing. I split up my 1,000 images so that I had a training set and a testing set, and I built the model using TensorFlow. So let's get back to our keynote, and we can get to our demo time. Awesome. Right. So let me pull up Google Colab. Okay. So I'm just going to adjust the screen a little bit so we can see what's going on. Okay, so if I come down here. Okay, so I've loaded up colab.research.google.com already. I've gone to the TensorFlow tutorial, and this is what we can see. So I'm just going to click on one of these buttons here just to make the screen a bit better there. And this is like a Jupyter notebook. So what we can see here is we've got these different either a text block or a code block, and we can run the code blocks. So if I come to this code block here, and we can discuss what's going on in this code block, I'm just going to click on that little circle there, and that's going to run that piece of code. So that piece of Python there says import TensorFlow as TF. So we've already got TensorFlow in our library. I've not needed to do pip install TensorFlow, which is what I would have to do if I was doing this in my own Python environment, and that's because Colab already has these libraries loaded. So import TensorFlow as TF, so we only have to refer to TensorFlow as TF in our code later on. Then we've got some helper libraries, so NumPy as MP, and that's for manipulating libraries, manipulating large data sets. And then we have matplotlib, pyplot, which is for drawing graphics in Jupyter notebooks, and we'll see why we need that in a second. And then we just say print the version number of TensorFlow. So 2.5 is the version that we're on, which I think is the latest version. Next up, we're going to import the Fashion-MNist Dataset that we looked at earlier. So these are the 70,000 grayscale images in 10 categories, and the 28 by 28 pixels here, and you can see an example. I've actually got the dataset loaded here. So if I zoom in on this, you can see there's loads of different types of clothing. I think there's some shoes as well, some trainers and some bags and some ankle boots. Okay, so that's what that looks like. So that's just an image that's embedded there. What we're going to do here is just run this next code block. And what that's going to do is it's going to say Fashion-MNist, which is our variable, equals tensorflow.keras.datasets.fashion-MNist. So Fashion-MNist is already a dataset that Keras knows about. And Keras is just another part of TensorFlow that enables us to play with datasets. And what we said there is train images and train labels and test images and test labels equals Fashion-MNist load data. So we're going to load, we're going to split it into the two types, and we're going to load into those different train images, train labels, test images and test labels. And we can have a look at what those are. So they are arrays of the training set. We can see there the labels. So we've got the t-shirts, we've got the trousers, pullovers, dress coats, sandals, shirts, sneakers, bags and ankle boots. And each image is mapped to a specific label. So that thing that I did where I drew the rectangle around it, they've already done that. They've already assigned the labels to each of the images in the data set, so we can just pull that in. And because we're just working with indexes, we're going to have another little helper array there, which is just an array of a list of class names of labels. So now we can explore the data set. So we're going to have a look at the shape of the data. So this is what the shape our tensor looks like. We've got 60,000 things in it, and they are 28 by 28 wide. So I don't say pixels because it's numbers. So there's 60,000. So this is essentially a three-dimensional array. So our tensor has got 60,000 objects in it. We know they're pictures. We know they're 28 by 28 pixels. Pixels are bytes in grayscale, so they're just values between 0 and 255. So likewise, there are 60,000 labels in the training set. So we can do the length of the training labels. We can see there's 60,000. Each label is assigned an integer between 0 and 9. So we can have a look at our training labels, and we can see there all the different numbers that are in there. There are 10,000 images in the training set. Again, we can look at that by clicking on the test images.shape. So there's 10,000 things, 28 by 28 That's the array dimensions, that's the shape of it. And we can have a look at the length of the test labels as well. So it's 10,000 test labels. Okay, now we can visualize it. So remember before we looked at matplotlib? Well, we can click on this little piece of code here, and that's going to draw out a little plot. So we say plot.figure. That's going to create a graphic for Jupyter Labs. We're going to do plot.imshow training image, and then the first training image which is the 0th one in the array. We're then going to do a little color bar there. So depending on the value of the value in the array, so between 0 and 255, it gets a different green value. So the darker it is, that's the lower the number, the lighter it is, the more yellowy or greeny it is. And then we're going to say plot the grid, frame false. We don't want to frame round it, and we just want to show the image. So that's what that little piece of code does there. So we can see there we've got a shoe. We recognize that as being a shoe. So we scale the image values of a range between 0 and 1 before we feed them into the neural network. So to divide the values by 255, that will give us this value between 0 and 1. That's the normalizing that we're going to do on that. And it's important that the training set and the testing set be pre-processed in the same way. So we're now going to pre-process both sets of data. Look how quickly it's achieved that. That's pretty impressive. It's gone through 70,000 images, and for each of the pixels in there, it's divided the value so that it's now a number between 0 and 1. So to verify that the data is correct in the correct format and ready to build our training network, let's display the first 25 images from the training set and display the class name below each image. So what we're going to do is going to create a new figure. This figure is going to be 10 by 10. And then we say for I in the range 25, we want 25 things, 5 by 5. We do a subplot 5 by 5. We're going to say I, which is our little counter there, plus 1. X ticks and Y ticks, it's said they're empty, grid's false. And then we're going to show the image, and we're going to also show the label name as well. So if we click on that, we shall get a nice graphic being produced by that piece of code. And we can see there's 25 images. We've got that ankle boot, we saw the very first one. We've got a t-shirt, we've got a shirt, top, dress, and so on. So we can see that's worked. So now we're going to build the model. We're going to use build the actual neural network. We're going to set up the layers. So the basic building block, if you remember, is those hidden layers. Layers extract the representations of the data being fed into them. And hopefully these are representations that are meaningful for the problem at hand. So depending on what problem we're trying to solve. So most deep learning consists of chaining together simple layers. Most layers such as TensorFlow, Keras, layers, dense, have parameters that are learned during training. So let's click on this here. And this is going to create our model. So what we've done there is we've said model is TensorFlow.Keras sequential. TensorFlow Keras layers flatten the input, and the shape of the things that we're putting in there is 28 by 28 because it's image data as pixels, but this is treating it as just arrays of arrays. So TensorFlow layers dense 128 activation ReLU. So that ReLU thing, we can have a look what that means in a second, I think, but that's the type of training that we're going to be using on this. And then Keras layers dense 10. So the first layer in the network is called flatten. This transforms the format of the images from a two-dimensional array of the 28 by 28 into a one-dimensional array. So 28 by 28 is 784. Think of the layer as unstacking the rows of pixels in the image and then lining them up. So the layer has no parameters to learn, it only just reformats the data. After the pixels are flattened, the network then consists of two layers. They're both dense layers. They are densely connected or fully connected, so every node is connected to every other node. That's what the dense means. The first dense layer has 128 nodes or neurons. The second and last layer returns a logits array of length 10 because there's 10 different labels that we're looking at. Each node contains a score that indicates the current image belonging to one of the 10 classes. So it's going to look at the image, it's going to crunch through all those different numbers, apply the weights to it, and at the end we should get a score for each of those 10 different outputs that logits array, and the one with the most number is the one which it thinks is that particular class, that particular label. So we're going to compile the model. So before the model is ready, we need to do a few more things, and we need to compile them. So we need to do a loss function. This measures how accurately the model is doing during the training. So to begin with, we've got a couple of options. We can either just throw random numbers into the weights, or we could start with 0 and work our way up. And this helps us steer the model. So what's this loss function, and how accurate is it during training? You want to minimize the amount of minimize the amount of loss you've got and steer the model in the right direction. We've then got this optimizer. So this is how the model is updated during when it sees data and it sees its loss function. And then we have the metrics, which are used to monitor the training and test steps, so we can see how accurate things are. So we're going to do the compile there. Again, that's quite a quick thing to do. The optimizer is Adam. I'm not sure what that one actually is, if I'm honest. The loss is Keras loss sparse categorizer cross entropy. That's the type of thing it's using. And then from logits is true. That means it's taking the outputs of them labels and then feeding it back in. So, and then the metrics is accuracy. That's what we're looking for. Right. So we're now going to feed the model. So to start the training, we call the model.fit, and it's called that because it fits the model to the training data. So let's click on that. Now this is the actual training stuff happening in real time. And this is the thing that when I ran my TwitcherPi, and I ran this on a MacBook Pro 2017 model, so it's pretty beefy as a laptop at the time. It took 3 days of solid 100% CPU to crunch through 1,000 images, but the images were varying in size, so it was having to look through each of them and find the various different things and then see whether they match the label or not. I probably could have stopped it after a certain amount of time, but I left it going because the accuracy wasn't sufficient. So you can see there we've done 10 epochs, 10 cycles through our training, and we've ended up with an accuracy of 0.91, which is not bad. That's 91%. So we can now evaluate the accuracy. So what we're going to do now is compare the model, how that performs against the test set. So we have the training set that we've trained the model on. We're now going to take the test set of data that it's never seen before, and we're going to see how accurate it does against this. So let's just do this. Again, it's just going to crunch through a couple of 10,000 images. And let's see how that does. So there we go. So against the test set that it's never seen before, it's 89%. So 91 on the training set, 89 on the test set that it's never seen before. So it's a little less than our training set, and this gap between the training accuracy and the test accuracy represents overfitting. So overfitting happens when a machine learning performs worse on new, previously unseen inputs on the training data. An overfitted model will memorises the noise and details in the training set to a point where it negatively impacts its performance. So we can tweak and adjust that in various different ways, but for today we're just going to look at how well it makes predictions about things. So the model is trained. We can now use it to make predictions about some images. So the model's linear outputs logits attached to a softmax layer to convert the logits to probabilities, which are easier to interpret. So let's do this then. And don't worry if you don't understand some of these terms. There's a lot of terminology in machine learning. You can just treat some of these things like building blocks for now until you learn more about it. Right, so it's run the predictions against the test images, and we can now see how well it's going to predict against each of these. So it's come up with an array of predictions. So the prediction is an array of 10 numbers. They represent the model's confidence. The image corresponds to 10 different articles of clothing. So we're actually going to show what these images are in a second. So we're now just going to look at the predictions. So the model is most confident that the image is an ankle boot, class number 9. And we can examine the test label to see if it was actually correct. So we can have a look at that. So yeah, it guessed correctly in that case. So now we can do another piece of code. So this plot image is essentially going to run through. We can run it and you'll see what actually it does. So it's going to oh, I thought it was actually going to show us. It's the next piece that's going to show us. So if I go to verifying the predictions, if I do this, it's going to show us, there's the ankle boot image, and they're the 10 different labels, and it's 99% sure that that's an ankle boot. So it's guessed correctly there. We can now do 25 different images, so we can, sorry, I thought that was 25 images. It's the next one that does that. So this one is a sandal. It's 90% sure this is a sandal, and actually it's a sneaker, it's a trainer, so it's not guessed that one correctly. So sometimes it can be really confident and wrong. So unfortunately that's something that can happen. So now we are going to plot out a couple of images and see how accurate and how well it does. So pullover, 100% sure, and it is a pullover. So you've got the guess there and what actually the label is. So trouser, it's 100% guess that. It's 100% guess that's trousers. It's 82% sure that that's a shirt. It's not quite sure. I think it could be some other things, but it's pretty sure. It's only the sandal that it got wrong. So out of, how many different things have we got there? So 15, is it? It's only got one wrong, so that's not too bad. So finally, the training model, we're going to use that to make a prediction against a single image. So what we're saying there, grab an image from the test data set, and then we're going to add the image to a batch where it's the only member. We're going to predict the correct label for this image. So that's the output. And then we're going to plot the value of that to see what it thinks it is. So it's pretty sure that this is a pullover. We can now check to see if in fact it was a pullover, and the model predicts the label as expected, so it's correctly guessed what this is. So that is how we use Google Colab to build a machine learning model from a data set. And the data set we can see there, and that's just a subset of the 70,000 images. So you can only imagine how long it must have, they must have had an AI to actually grab the image and correctly sort it, unless they had a data set already of very nicely cropped images. Converting them all to grayscale, you could do that in NumPy. That's the kind of thing that's very good at doing. So it could take any size of image and resample it down to 28 by 28, for example. But you can see that works in real time. We've trained our data set and we didn't need to wait days and days for that to actually crunch through. So I'm pleased with that. Okay, so let me just jump back to our keynote for a second. So for the next steps with TwitcherPi, what I want to do there is build a web UI for this. So one of the issues I came up against, I trained after spending weeks on this thing. It was great at getting a picture off the internet and saying if there was a bird in that image and what type of bird that was, as long as the bird was either front on, side on, or other side, but not from the back, because who takes a picture of a bird from the back and puts it on the internet? No one does that. However, if birds are eating at a bird table, you might get the back of them, or some back quarter of them or something like that, and there might be a few of them on there. So it didn't work very well, other than for nicely taken professional pictures of birds, because that's what it'd been trained on. So it's kind of overfit for that. So what I want to be able to do is point a camera at a bird table and have it left there for a very long amount of time and take pictures whenever there is something in the scene. So how do I get it to detect that there's something in the scene? I need to have something detect that there's an object there. So we could use a neural network for that. I then need it to save that image to a location, so I can then go in later on and draw that rectangle around it, correctly label it to build up a new set, a more accurate set of data, and then I can use that to train a better model. But I only want it to take a picture, say, every 5 seconds. We don't want it to take the same picture thousands of times a second. I don't want a movie of this, because it would just fill up, a hard drive of any size very quickly. And once I've got this working for, I think, maybe the top 20 different types of bird that we find in the UK, then it'll be something of use. We can open source this and probably share it with something like the RSPB. So I want to allow users to submit their own pictures and choose a label from that top 20. And then I obviously need to buy a bird table. I haven't got one in my garden at the moment. I did have one, but we've rearranged the garden when we built this summer house. So I need to buy a new bird table, get a Pi camera pointing at it, which is quite convenient to do actually now. Pointing over there because that's where the window is. So that's what I need to do next. So I wanted to give you an update about a couple of things. So the first one, the Small Robots Facebook group. So we have now got over 11,000 members in this group. This is insane. I only started this last August, so about a year ago, and it's gone from 0 members to 11.2 thousand members, which is just crazy. So I want to keep this to be the best place to share, discuss, learn about building small robots on Facebook. So that question before you asked about, am I on Discord? This is where I prefer to hang out. This is my own created area. I don't have a lot of time. Discord's quite time hungry. It wants you to have sort of conversations there and then, but I'd rather do that here. And we've got a whole group of different people in that group. One of those members is 87 years old and he's just getting started in robotics. How awesome is that? Just getting started in it. I love that. So if nothing else, that underlines the point that you're never too old to learn robotics or programming. You can just get started with this from any age. Love that. So YouTube, another major milestone. So you can see all the different videos there on the right hand side there that we've created over this past year. So I've been YouTubing for 1 year. This is my first year of YouTubing. You can go back to look to that very first video where I'm sort of showing you how to build a SMARS robot using Fusion 360. I'm sat near my staircase and yeah, it's not the best video, but it was a start. So that's where I started from. Since then, we've had 54.4 thousand views. That's how many people have looked at these videos. There's 109 videos in total currently on the YouTube channel. There'll be 110 from today. And we have, that number has actually changed already. So we've got about 1,895, I think it is now, subscribers to the channel. We're nearly at that 2,000 subscriber mark as a milestone. And we have over 4.2 thousand watch hours, which again is just crazy. That's how much time people have spent watching this stuff. Insane. So I'm thankful so much that people have been able to join me on this journey and have taken value in doing this. So I'm looking forward to growing this even more over the next year. So that was just a little update I wanted to give you. Okay, so let's get over to some of the comments that people have been making. Let's have a see. I'll see that there's quite a few different comments coming through there. So Tom was saying, nice to see you after a short break. Yes, so I was away for 2 weeks. Sorry, there was no videos during that time. So he's going to enjoy the show later. He's going to get the kids back to bed. Hi, Auntie Marlene. She's the very generous person who donated that and that to me. So that's an oscilloscope and a BBC computer from back in the day. So Ovi was asking a question, can you use this for more than 3 purposes? You can use machine learning for anything you can think of. Any kind of problem where you have something that requires either classifying or something that computers are not traditionally very good at. You can throw machine learning at it if you think about it enough, using things like TensorFlow to build a model. So you said that e.g., oh, you didn't give me the example actually. You said e.g. and then you haven't got to the example. And you said, what's better, TensorFlow or Jupyter Notebook? So TensorFlow is the framework, the library that's been produced by Google for building machine learning models. So it's a whole set of things that you need to do to things like the tensors themselves, you know, the multi-dimensional arrays, things like manipulating them arrays, like when we did that pre-processing on the very first layer where we took the 28 by 28 and stretched it out and flattened it to a 784 pixel array. Things like that, TensorFlow is just perfect for. So that's what you want to use TensorFlow for. It's a library. Whereas Jupyter Notebook is a Python environment. So it enables you to create little code cells or, I mean, if we just load up, for example, very quickly, let me just grab that Colab environment. Let's go for a new one. just going to share my screen in a second. Right. So if I've got Colab open here, and what I'm going to do is I'm just going to create a new notebook. So let's just do that. And it's just thinking about that for a second. And this is a Python library. Right, here we go. So we're now in our Python Colab environment, which is just Jupyter Notebook. So we can either type code in here like a equals 1, something like that. We can then run that, and it has to initialize itself first. You can just see there. We can then do another piece of code where we just say print a, something like that. We can see that's now a value 1. We could have could be a text block. So we could say, and we can use Markdown in here. So we can say, hello world, this is some great documentation. Something like that. There you go, and it's giving you an example of what that will actually look like. So then we can do another code block, and now it's converted that piece of Markdown into an inline piece of documentation. So it's useful for educators if you want to walk people through a piece of code. So if you're teaching your students, for example, over how to do things in Python, you can litter your code in the Jupyter Notebook using Colab. You can give them helpful tips and tricks and things like that. And what I like about it is you can see and you can rerun these code blocks. So you might think, well, let's just change that to 2. What happens then? And then we run that next one. That's 2 there. Or we can change that so that it actually prints out A there. And then this prints out A plus 1, for example. We can then rerun that. We've got the output. We've got the output of that one. We can just interactively change our code in a way that's easy to see. It's much more difficult if you think about how you'd code like a Pico or a microbit where you've got to go back into the thing, upload it. This is far more interactive. So that's what you can do with Colab. It's a Python environment using a Jupyter Notebook. So you can, if you open up this here, you can see your table of contents, which is picking from these different styles here. So if we go back into there, you could do some lists. So this is like a list item 2, list item 3, and so on. You can see there you get bullet lists just by using that kind of markdown. If you do 3 underscores, you get a horizontal line like so. If you do 1.1.1 point and you have, I don't know, item, you get a numbered list, even though the actual numbers on there are just 1s. It knows what to do with them, and so on. So Markdown, if you've not used that before, is great for documentation. So that's what you can do with a Colab. You can create notebooks. If I just bring this back down so we can see the file menu, you can either save that to Google Drive. So if you've got a Google Drive, you can save it to there. You can save it as a GitHub gist, which is like a little code snippet. You can save it as a GitHub repository. It'll upload it to there, or you can just save it out. I think you can like download it, cut and paste it, that kind of thing. And you can clear all the outputs. So if you have got all these little outputs here, you can go to edit, clear all outputs, and it's as if it's never run that before. You can see here as well, you've got the RAM and disk. So if you click on that, you can see how much resources you're actually taking up there. So you can see we're not using very much RAM, we're not using very much disk. I think you get 12 gig of RAM, which is absolutely tons. You can see there 12 gig of RAM and 100 gig of space. So tons of space. Okay, so that's Colab. That's what you can do with that. Let's have a look again at some of the other comments. So somebody said there, Ian and Kevin, finally got some time to join you. Good stuff. And my cousin Jackie, hi, how you doing, Jackie? So Richard said, had visitors who left, so thought I'd say hello and hope you enjoy your break. Thanks, Richard. Appreciate that. And he's bought a Pico starter kit from Amazon. Awesome. Might even try and use it in future. The starter kit even. Awesome. Spell check. Spell hexum. What does that mean? I'm loving the Wallace and Gromit stuff you've got there as the image on your Facebook profile. Cool, I think that's all the comments there. I'm appreciative there's a football match that some people want to go and watch starting now, so I shall bid you adieu and I shall see you next time. Hope you found this video useful and I shall see you next time. Thanks everybody. Bye for now.